Welcome everybody. My name is Gonella Diaza, and I'm an in silico expert in the QSAR team at Germany GmbH. After a short introduction on the available models and on the current case study, we will see how to run VEGA and to analyze the results, how to use the DanishQSARdb database to extract QSAR results and to analyze them, and also how to document the QSAR results in Euclid for each dossier preparation. So briefly on the case study, as said today, the aim is to predict in vitro gene mutation with 2 QSAR models and document the results in Euclid. Our target molecule for today is 2,3,4-3-chlorobiphenyl, and we will use a knowledge-based model from VEGA, the mutagenicity Ames test model by ISS, which is an implementation of the famous Benigni-Bossa rule set, and a statistical model, which is in reality a consensus model called battery model in DanishQSAR database. And the input for the two tools will be the SMILES notation of our molecule. So the gateway developed by ConcertReach, which is accessible in the results section or through the direct link shown on screen, currently include 22 models from VEGA and DanishQSAR database for evaluating in vitro gene mutation in bacteria. And the gateway provides an overview of several characteristics of the models, the type of model, the data set, size, training set, and test set size, cross-validation procedure, the platform in which the model is implemented, and a direct link to the model documentation in the QSAR model reporting or QMRF format, which is then useful for documenting the model in the Euclid entries while preparing the dossier. Now, a quick overview on all available models for in vitro gene mutation in bacteria in the gateway. So the gateway includes links to 4 VEGA models of different nature. We have a SAR model, which is a hybrid model, which means it includes submodel for statistical evaluation and for knowledge-based evaluation, a read-across automated model, the knowledge-based model we'll use today, and a statistical model based on structural alert called SAR-PI, ERFM. The DanishQSAR database includes 15 statistical models for covering the bacteria reverse mutation, so in vitro gene mutation in bacteria, and if the result of this model is positive, meaning mutagenic, and the molecule is evaluated as an in-domain, then possible mechanism can be investigated using 3 statistical models for each effect. Plus, in the DanishQSAR database, there are also the so-called battery model, which are consensus model, for the main endpoint, which is the one we'll use today for our case study, and a battery for each mechanism of action, each battery model summarizing the results of the 3 statistical models for each endpoint and mechanism. The DanishQSAR database also includes 2 knowledge-based profilers from the OECD QSAR toolbox, DNA alerts for Ames by OASIS, and in vitro mutagenicity Ames test alert by ISS, which is actually implemented based on the same Benigni-Bossa rule set as the model in VEGA. So I can anticipate a question how to select the appropriate model for my substance. Well, I have to say that this is not in the scope of today's presentation, but I want just to give you some quick information about this. So in general, an a priori selection is not possible. However, experience in using the models might suggest which could give more reliable results for certain type of substances, for example, industrial chemicals, active substances. For selecting and evaluating the reliability of the result, information on the compliance of the target model with the applicability domain of the models is important to consider, as well as a comparison with similar molecules, meaning a comparison on how the models perform on the similar molecules. And in general, it is required to use multiple and different models for evaluating the same endpoint, which is what we are doing today in the case study. So for selecting the most appropriate models or results, an expert analysis is needed. And the good thing is that both tools we'll see today, VEGA and DanishQSARdb, provides information for performing this expert analysis. So we can now move to how to run VEGA and to analyze the results. So VEGA is a freely available platform developed based on contribution from EU projects by Mario Negri Institute and Code in Italy. It currently includes 110 statistical and knowledge-based QSAR models for prediction of ecotoxicological, toxicological, environmental fate, and physicochemical properties of chemicals. Now, running VEGA is quite easy. The software is designed to be user-friendly, and it's designed as a 4-step procedure, with the first step being inserting your molecule. We did it in this example using the SMILES notation, and VEGA displayed the structure of the inserted SMILE to, for example, double check that the included SMILE is correct. The second step is selecting the model to be run. In this case, I selected the model for today's case study. Then the type of report to be generated can be selected. We have, in general, 2 types of report, PDF and text, with the PDF including all information from the from the result, so the prediction itself, the applicability domain evaluation, similar molecules, and so on. While the text file is generally more useful for example, exporting results from multiple models run on multiple molecules and import it in Excel. Finally, the user just has to click on the predict button, and the selected model is run and the report is generated. Now we can have a look at the report generated by VEGA and how to analyze it. So the report has a prediction summary, actually the first page, which includes a section where the outcome or prediction is represented using a color code, for example, red for toxic, green for non-toxic, and the reliability of the prediction is represented using a 3-star format, where 1 star means low reliability, 3 stars means high reliability. And below is also provided a summary of the evaluation. More details are also provided in the first page, for example, the SMILES, again, the outcome, and of course, if structural alerts have been identified for our substance, no alerts have been identified. And what I would like to draw your attention on is that the reliability assigned by VEGA is based on an automated check of the compliance of the molecule with the applicability domain of the model. Now, coming to the applicability domain, VEGA uses several parameters to evaluate the compliance. And these parameters also depends, the number of these parameters and type depends on the model. So what we see on screen are the parameters used for this specific model, the knowledge-based model for Ames test by ISS. And for this model, VEGA evaluates how similar are the 2 most similar molecules from the model's dataset, the accuracy in predicting those similar molecules, the concordance, which means if the prediction generated for the target is comparable to the experimental value available for the similar one. So these 3 parameters are all based on the 2 most similar molecules for this model. And also, VEGA check if all the structural features of the target model are represented in a training set. For those of you who are maybe familiar with DEREC, this is similar to the concept of unclassified features. And based on this parameter, VEGA calculates a so-called global applicability domain index for evaluating if the molecule is compliant or not. which is actually a number, and there are thresholds set, which are also model depending for deciding if the molecule is compliant or not. For example, for this specific model, if the applicability domain index is higher or equal to 0.9, then the molecule is compliant. In our case, we see also from this exclamation mark symbol, there is something, let's say, not really good. Exclamation mark in the end means that the compliance is not perfect. It doesn't mean not compliant. And we also see that the parameter influencing this is the concordance.
Now, to analyze the result and understand why the concordance, for example, is not perfect, we can consider the similar molecules provided by VEGA. And we need to keep in mind that for this model, VEGA considers the two most similar molecules for calculating the applicability domain parameters. And we can see that the second one is experimentally mutagenic, while our is predicted as non-mutagenic. And that's why the concordance is not perfect. But we can also see that for this molecule, a structural alert is identified for mutagenicity, and the same structural alert is not present in our molecule. So if we possibly exclude this molecule from the comparison, let's say, and we also consider that all other reported molecules are experimentally non-mutagenic, we might be able to reevaluate the reliability assigned by VEGA and possibly increase it. So take-home message from VEGA. VEGA provides full documentation on all models in QMRF format and provide also supporting information for evaluating the results. So for example, the applicability domain compliance and the similar molecules. And this allows expert evaluation. And all this information is relevant when preparing the risk dossier, so when preparing Euclid entries. We also saw that the applicability domain is affected by the identified similar molecules, that the current similarity evaluation does not consider important parameters, for example, difference in alerts, and therefore the automated applicability domain compliance check is not perfect and requires some user critical check. But to be fairly honest, this affects other tools as well, including commercial one. We will see in the next presentation today that a novel tool called Vera has been developed aiming also and improving the software related to these issues. We can now move to using the DanishQSAR database and again analyzing the results. So the DanishQSAR database is a freely accessible online database, currently including a little over 650,000 chemical as monoconstituent structures. For each single structure, the database is able to generate a report upon user request, which contains more than 200 QSAR results. And the database also offers some advanced searching tools for identifying potential similar molecules, which can be used for supporting QSAR prediction or, for example, as candidate analogs for read-across. I would like to highlight the difference between the DanishQSAR database and VEGA. While VEGA runs the model, the selected model on the target molecule, the DanishQSAR database search if the target molecule is present in the database and then extract already generated QSAR results. Now, using the database, the DanishQSAR database is also quite easy, and it's also a user-friendly tool. So the structure can be input as smile notation, as we see here, and using the smile, the database can be searched for in this case, we use the exact match search, meaning we want exactly this structure. But of course, we can use different other type of search, like search for substructure or search based on similarity.
If the target molecule is included in the database, as for our case, then it is possible to download, to generate and download a report including all the more than 200 QSAR results. And what we see here is a cover page. Coming to the results for in vitro gene mutation in bacteria, as mentioned at the beginning, we have multiple statistical models for Ames test and the different mechanism, and also the battery. Thanks to the collaboration within Life Concert Reach, the results from the VEGA models and the consensus model have been integrated as well recently. And finally, as mentioned, we have also the results from the two profilers from the OECD QSAR toolbox. Now, for identifying the similar molecules, the DanishQSAR database does not provide this information automatically, but as mentioned, it includes tools for doing this, and it's a kind of stepwise approach. So DanishQSAR database can be searched for molecules based on available experimental data, QSAR prediction, structural alert, etc. So in our case, for example, we are interested in identifying both positive and negative molecules for Ames, so based on experimental data. And since our target molecule has no alert for DNA binding or for in vitro gene mutation from this toolbox profiler, we want to also identify molecules with the same no alerts profile to somehow account for mechanistic similarity. For each query, so for each search we make, the DanishQSAR database retrieve a list of molecules, and this list can be merged using the logical operator and OR. I will not show the full procedure, but I included some additional slides at the end of this presentation, which you will be able to see when the slides will be distributed. So this is an example of the result. So as mentioned, for each search or each operation we make, the DanishQSAR database generate a list of molecules. With the first one, in this case, is the exact match, so our target molecule. Then we search for all molecules with available positive experimental data for Ames test, all molecules with negative experimental data for Ames test. Then we search for the 4 profilers, so the 2 for mutagenicity and 2 more general mechanistic for DNA binding in general. Since our target, as mentioned, at no alert, we search all molecules with no alert for these profilers. And then we went on by merging the search. So the first merge is we create a list including the target and all molecules identified with experimental data. And then we filter out those molecules which has a different alert profile compared to the target. And this is an example of the obtained result where the list can be sorted, for example, by calculating the structural similarity to our target. And one can also include additional information as columns in a kind of data matrix, for example, about the experimental data available, the results of the model we want to investigate, but also, for example, in case molecules with different alert profile want to be kept in our overview, we can also include the results of the profiler to see if there are different alerts in the molecules. And for example, for this overview, we see that all identified similar molecules are experimentally negative and correctly predicted by the battery, and they're also in the domain of the battery. This maybe it's not the best example. As we can see here, they're not really highly similar, but there are also molecules with multiple chloride substituted as for our, which are also negative and predicted correctly. Now, some take-home message again. DanishQSARdb provides as VEGA full documentation of the models in QMRF format, supporting information, for example, applicability domain, compliance, similar molecules, is either provided or can be retrieved, which allow expert evaluation. The identification of similar molecules, as we've seen, is not automated. However, the DanishQSARdb provides tool for including more information, for example, compared to VEGA, for identifying similar molecules, for example, considering the alerts profile. And the generated reports do not include the full applicability domain compliance evaluation. It's just information in or out. However, the QMRF includes the definition of the applicability domain, and this can be used then for documenting the results, for example, in Euclid. Now, coming to the last part of this presentation, which is documenting QSAR results in Euclid for rich dossier preparation. We will use as example the outcome of the VEGA model, and we will document it in Euclid according to the ECA practical guide, How to Use and Report QSAR of July 2016. So, and we are using, of course, the web client of Euclid, which is now the official one. So, well, regarding the administrative data, the endpoint is not strictly related to QSAR, but I just selected the correct endpoint predicted by the model. Type of information should be QSAR. The adequacy of results, according to the practical guide, can be key, weight of evidence, or supporting. However, for human health endpoints or toxicological endpoints, using QSAR as key is probably not the best choice. I would say that QSAR results can be used either in a weight of evidence or as supporting information. For reliability, the practical guide clearly states that normally it's maximum 2. And Euclid provides in the rationale a pick list with some items related to QSAR results. For example, the molecule is in domain and with full documentation, or not fully in domain with full documentation, and so on. Now, coming to the field justification for type of information, Euclid provides a template for reporting QSAR results with all the information needed, let's say, for documenting the results. So, for example, the software should be stated. In our case, is VEGA and its version. The model, mutagenicity, ISS, and the version. The SMILES used for the calculation. Regarding the scientific validity, QMRF can be attached and reference can be made to it. For the applicability domain, again, in the case of VEGA, the report can be attached. It includes already all the information for the applicability domain evaluation. However, if an expert assessment is performed, as what we've seen, for example, this regarding one of the similar molecule, this explanation could be included here. If we are using the DanishQSAR database, the procedure for selecting similar molecules, for example, the one I showed you before, can be also documented here. And finally, for the adequacy, an expert assessment is needed. As mentioned, the QMRF can be attached in the attach justification. Currently, none of the two tools we've seen today, VEGA, DanishQSARdb, generates an automated QPRF. If a user generates a QPRF on its own, it can also be attached in this section. For the data source, according to the practical guide, only basic information about the model has to be included, which is software name and version, model name and version, year of publication. For the test guideline, the practical guide gives two possibilities. One is to mention the rich guidance on QSAR. The other is to mention the test guidelines used to generate the data included in the training set of the model. And in the principle of method, the publication, let's say, behind the model can be included, and this information is usually present in the QMRF section 2.7. Finally, for the test material, the practical guide includes some specific rules, let's say, or requirement. So when documenting QSAR result, the test material should be the structure predicted with the model. So in case, for example, of a substance composed by multiple constituents, UVCB, multi-constituent substance, or in case impurities are evaluated, the test material should not reflect the substance, but the constituent. And this also means that, again, according to the practical guide, one is required to include one Euclid entry for each QSAR, for each constituent evaluated with QSAR. The practical guide also required that the SMILES is stated in the specific details on test material. And for the result, the practical guide doesn't give you any information because the practical guide is in general for all endpoints. However, I just want to mention that in the remarks on result, there are some, the pick list include some items specific for QSAR. And with this, I conclude my presentation today. I would like to thank Nadine Sickinger and Milena Gilwald from the Gonella Academy team, Giuseppe Raitano from Mario Legre Institute, Eva Bay from the DanishQSAR database, and all partners of the ICONS Research project, Katarzyna Bucher and the QSAR team at Gonella, and the speakers of today and of the next web seminar, which is on 31st of May.
And of course, all of you for your attention. Again, thank you very much. I hope you found this presentation interesting. And for question and answer, we will have a session at the end of the next web seminar. Thanks again.